All right, thank you. So can you hear me? Great, fantastic. So my name is Torbjörn Törnkvist, or Toby, Tobbe for short. So I'm going to talk a little bit about Openflow and the work I've been doing in that area the recent months. It's called Tailflow. So I'm working for a company called Tailflow, founded in 2005. And I've only been working there for 1 year now, but it's run by lots of my old buddies from back from Ericsson, so I know them quite well. They have two products called NCS and ConfD, and I will mention them a little bit because the whole work I've been doing is supposed to fit into those two products that they are producing. Lots of customers, operators, and manufacturers all over the world. So it's sort of two parts. I have to set up the scene a little bit. So I'm going to talk a little bit about SDN and what that is and what I think it is and where Openflow fit into SDN. And then I'm going to dive into Tailflow a little bit more explicit to show you how it works, etc. So network management. I won't talk that much about network management. But network management, every one of you probably know or have a feeling for what network management is. You manage your network, sort of. And it's kind of tedious work where you have to work with CLIs, etc. And and for large operators, that often is a very costly sort of way of implementing new services, because you have to do lots of manual work in worst case. And worst case is often the normal case. Or as I have been told. So I'm not coming from the network engineering side. I'm coming from the software engineering side. So, but I want to talk a little bit about not this traditional view, but network management with a twist, sort of. But what's important to realize is that network management normally requires lots of tedious manual work, which is very error-prone. I mean. Imagine if you're a large operator and you have a customer that wants a new VPN leg, for example, you have to set it up, and that might be realized by manipulating a number of network devices, etc. And if you get something wrong, you have to sort of go back and find where the error were, and etc. And it's all a very costly process. And so that's where SDN comes in. Because when you have a very complex system like a large operator, you have a huge network, very complex. And in general, when you deal with software which is very complex, you sort of try to cope with that complexity in some way. And the normal approach is to abstract in some way. So if you have this huge complex system, you sort of can take a bird's eye viewpoint, for example, to outline a couple of large components and how they sort of are connected and interact to each other. And then you can zoom in on one of the components, and then suddenly other subcomponents appears within that component. So you have various layers of abstractions to be able to cope with that kind of complexity. So what if you could do that for network management, so that you could abstract and the network sort of itself, and to be able to apply sort of modern software engineering technique to that kind of problem? The answer, of course, as I think, is yes, because as I'm going to show you on the next slide, we can actually do that. But the result of that is that we can reduce time to deployment when you, for example, add this new kind of service like this new VPN leg, for example. And in the end, what it all boils down to is to reduce costs. So here's a sort of a jam-packed slide. But what it shows is the Tailflow product called NCS up here, controlling a number of network devices, firewalls, switches, routers, etc., from various kind of manufacturers. So by introducing a kind of abstract model of each of those devices, how they work, you can actually start doing interesting things. If you have a way of modeling that, you can represent it as data structures, for example, and you can start manipulating them and doing interesting things. So And that's exactly what we are doing at TLF. So the way we are modeling things is by using a modeling language called Yang, which makes it possible to model those kind of network devices. We can bring them into our system and represent them internally in various kinds of data structures to make it possible to, for example, manage a number of heterogeneous network elements as one single homogeneous system, so that you can manipulate many of those devices in one consistent way. And by representing stuff like this as data structures, you can starting to do things which is sort of normal when you come from software engineering side. For example, you can sort of auto-render CLIs. You can introduce concepts like transactions, for example, so that we can actually introduce changes into the network as on a transactional basis. The other product that TLF is doing is producing is called confd, and that's actually a thing that you can put on a network device. So southbound down from the confd, you can have lots of hooks which you can integrate into your product, your network device. And describing that device with this model makes it possible for confd to auto-render like network management APIs northbound, like netconf, or CLIs, or REST interfaces, GUIs, etc. So down here we have network elements, devices, and up here we can control them in a consistent way. So that's the way we are using the abstraction to apply that onto this complex world down here. But we can take that kind of abstraction to yet another level, which we have done with this product NCS. So we can introduce something called a service model. So for example, this VPN leg that as mentioned, we can represent that thing, that service as a model. So we can have that model, the service model for the VPN service. Then by adding some kind of mapping logic, we can actually take that service, break it down, and in the end we sort of spit out all the kind of commands that needs to be done on all those devices to set up this new service. And when I started reading about SDN, I thought SDN has been sort of this word which has come up quite sort of recent and become very hot. So I thought, but we have been doing that for quite a while now, but we didn't call it SDN. But this is really what I think is SDN, how we, by using abstraction and software engineering techniques, can get a hold of the complexity of a complex network environment. So for me as a programmer, it's very easy to get excited. All right, I can program the network. So I put this slide up just to remind myself, at least, that it's not really about the programming the network. It's the services, the network services that we want to program. That's the important thing, because that's what makes the revenue at the end. So now let's see what Openflow is. We can relate it to SDN. And for me, a router or a firewall is a sort of a pizza box you buy on the shelf somewhere. And it's sort of, to my imagination at least, it consists of some hardware and some software that controls that hardware. And if you move that software outside of the box, and then you figure out sort of a protocol so that this software can talk to the hardware, then you have Openflow, because that's what Openflow is. Openflow is a protocol from this software to control this sort of general hardware thingy. And the software in the Openflow terminology is called an Openflow controller. So how does it work? The hardware is very simple. It's sort of like a forwarding table, as we heard the previous speaker talk about a little bit. So like Ethernet packets is coming into the hardware switch, like that. And the hardware looks up in the forwarding table, what am I supposed to do with this packet? It tries to match sort of the packet, various kind of packet headers in the protocols that is coming in from Ethernet, for example. You try to match that, and then you try to figure out what to do. For example, send it out on another port in the switch. So if you don't find anything in your forwarding table, what are you going to do? Well, you have to ask someone, and you're going to ask your controller, your software, what am I going to do with this packet? And the software is going to figure out that, OK, it's a Ethernet packet who's going to go to a certain source address, so let's send it out on that port. So it's going to tell the hardware, send it out to that port. And it can also install a flow describing this kind of operation into the hardware so that the next similar packet won't have to go up to the controller because it makes use of the existing flow entry and sort of finds its way out. So that's basically the essence of Openflow. So this is just a little bit more detail about the matching. So this is sort of a sketch of how a flow table entry look like. So you can match, when packets come in, you can match on the sort of ingress port of the switch. You can match on the Ethernet source, destination address, the IP source, desk, TCP, UDP ports, and some other stuff like VLAN tags and stuff. And when you find a match connected to that flow entry, you also have a set of actions. What are you going to do with this packet? So for example, you can say that I want to send out this packet on a certain port, or I can say that, hey, I want to rewrite some of the headers here. I want to rewrite the Ethernet source address and then send it out to some port. Or I might say that, hey, this packet shouldn't be allowed to continue through this switch, so I'm just going to drop it, no actions at all. Just drop it on the floor. So that's basically how it works. But to me, who comes from Tailflow, where we deal with this network management problem, I want to be able to manage this kind of device. To me, it's just a device. An Openflow application is just another device in the network, which has to be able to live and coexist with other kind of traditional network devices. So, I mean, you have this management interfaces here, netconf, SNMP, CLIs for those traditional network elements. But if you write some kind of Openflow application, to me, it's also just another device that needs to be managed, either through this software in some way, or perhaps we should put some of the management straight on the Openflow protocol level. It needs to be managed. So to me, Openflow is a component of SDN. It's not SDN. Openflow is not the same as SDN. It's a component of SDN as I see it. So that's how SDN and Openflow relates to each other in my mind. So when I started to look into this, I wanted to figure out how we can deal with Openflow devices or Openflow applications. So I started to read up on the protocol, of course, and tried to figure out how to do it, and started to experiment with implementing sort of simple programmer patch panels, some simple load balancers and stuff. But it is all very low level on the protocol level, so it's like assembler sort of. You have those flow table entries that you're sending down to the hardware. So actually structure the software was a major problem that I wanted to be able to manage it. I had to sort of come up with some idea of how the software could be structured. And I tried to find information on the net, and most of the examples sort of stopped with a trivial learning switch example, and then you were on your own. So I couldn't really find any approaches on architectures for how to write Openflow applications. There were some research papers that I found out about, but not much. And for me, it was also very important how to do management, network management of those kind of systems in a sort of consistent way. So the Openflow controller, the actual software, from its point of view, the switch just generates lots of events, not lot of events, like sort of perhaps 10 events sort of. And the most common one, of course, is when a packet don't match any entry in the flow table down in the hardware. Then you get this packet in event from the switch to the controller, and you have to act upon that. But you can have other kinds of events. For example, when a new switch connects to the controller, you have this data path join event. Or when a flow times out in the hardware, because every flow is attached with a timer. Then you can get an event where, hey, this flow entry timed out and has been removed, so you can act upon that. So there are a couple of other events too. But what you want to do when this packet entries is to apply some kind of logic onto this kind of event to create some kind of reaction. It might be that you want to drop the thing, but you need to act upon that event. So when I wrote my small experiments, sort of, as usual, I was thinking in a functional programming way, where I sort of tried to, by solving the problem, I always sort of solve a little piece and then put the rest of the problem down into the next function, and then you sort of continue like that to abstract the sort of problem in various layers. But after a while, I started to think about some experiments I did for like 15, 20 years ago when I was still at CS Lab at Ericsson. Because at that time, it was kind of a research topic around something called microprotocols. So Cornell, for example, they had a microprotocol framework called Horus. And there were actually a book written called Computer Networks by Peterson and Davey, which described the X kernel, which also was a sort of microprotocol framework. And the basic idea was that normally you have those kind of huge, large protocols like TCP, IP, etc. But instead, try and break out sort of a minimum sort of amount of logic that makes sense. For example, you could think of sliding window as one little piece of a protocol, a microprotocol. Or you could think of fragmentation or reassembly of fragmented packages as one sort of microprotocol, and put them in a graph. And that, as a whole, forms your sort of protocol. So I did some experiments around that for 15, 20 years ago, and I started to think again now, perhaps that could be something that I could use here. So I started to try to build something. So I came up with this name, Flowlets, to describe this kind of microprotocol. So here we have a stack of Flowlets, which implements sort of a virtual layer 2 network device, sort of the control software of such a device, as a switch with the capability of supporting sort of virtual layer 2 networks like VLANs. So we have a number of Flowlets, and when an event occurs or enters the controller from the switch, we send this event through the stack, and each Flowlet are able to look at this event and take some actions or just ignore the event. So in this case, we have like 5 Flowlets here, and they are each doing just a small amount of work to keep them simple to understand and simple to write and simple to debug, etc. So the first one, called the Mac learner, for example, it just snoops the incoming packet and stores, okay, I see a packet coming on that ingress port from that MAC address. Let's store it into a database for later use for anyone else. For example, other Flowlets can make use of that information. So that's the only thing it does. And then a packet can continue to flow through this stack of Flowlets. The next Flowlet, the ARP replier, makes it possible to act as an ARP proxy, for example. For example, if your application here wants to act like, for example, a default gateway or something. So someone is asking for your IP address. Then you can say, hey, gonna answer to those kind of IP addresses here for ARP requests. So it's the only thing that Flowlet does. And then we have the layer 2 filter. That was the most sort of complex one of those 5. So it makes it possible to introduce some kind of filters for to decide whether a packet should be able to continue down in the stack, or if it should sort of drop it, or it should jump to another stack, because I actually introduced After a while, I introduced the possibility to jump to name stacks like this, and then I could jump to other stacks, sort of inspired from IP chains, where you can do that. And assuming you are able to continue down through this L2 filter thingy here, you come down to the ARP Flutter flowlet, which only has one thing to do, one task to do, and that is to sending ARP requests, which we don't know anything about, send them out on all the ports on the switch. And the last flowlet here, the L2 flow maker, whenever it gets a packet in, it just connects the ingress port with the egress port and makes use of the information we have in this Mac database. So each of those are doing just a very simple thing, but together they form this sort of learning switch with this virtual layer 2 capability. So I wanted to explore this and try to write some kind of proof of concept which was enough complex to see whether I could sort of, if this was a reasonable approach. So I actually did that, but before I'm going to show you that picture, I'm going to tell you a little bit about the components in the Tailflow system. So the flowlet itself consists of the Erlang code, the Erlang module which implements the actual logic, and then the configuration which is specific for that flowlet is described in a Yang module. And Yang is this modeling language I was telling you about. So the flowlets then are sort of ordered in this kind of execution stacks. And when a packet enters through this stack, the flowlet can sort of decide by returning either of those three possibilities here. The flowlet, when it's executing, when it has finished to execute, it can return break, which means that, okay, do not continue to execute the flowlets in the stack. Stop executing, we are done. Or it can say continue, and that means, all right, continue, call the next flowlet in the stack. Or it can say jump to another stack, and continue executing. Each flowlet has a local state, which is maintained by this Tailflow controller. So at the startup of the system, each flowlet is called by this controller, which makes it possible for it to read its configuration from a configuration database, store that into some kind of local state, which then controller maintains. So the local state is injected into the Erlang module for each call, and then it's retained by, well, it might have been modified by the module, so it's retained until the next call. There's also an event state, so actually during the lifespan of the event, you can actually have a state which lives through the stack of flowlets, but then are discarded. The other key thing here is something called the switch logic. And the switch logic is actually what defines this, that is actually the Openflow application itself, the complete sort of Openflow device software that we have created. So it contains of all those flowlet configurations and all the stacks. And the thing is that the controller can, of course, work with lots of switches. So you can apply this software, which is called the switch logic configuration, can apply that either to a particular switch by using of this unique identifier from the switch called the data path ID, or you could apply it to any other switch which doesn't match any data path ID. So if you look at a little picture here, so to the right we have the Openflow switches generating events coming into the Tailflow controller. This switch logic is looked up by looking at the data path ID, which comes with the event, and then we apply the correct sort of stack of flowlets we start executing here. Northbound, so this is sort of the Tailflow controller device, so to say. So it makes use of confd, which is this product from TLF, because northbound we will have this kind of interface with netconf, CLIs, REST APIs, etc., so that it can be managed in this kind of environment. If you remember this picture I showed before, where all the network devices were at the bottom and NCS at the top, managing all those kind of devices. So this forms a networked device, which may deal with lots of different kind of software applications for lots of different switches. So, but on this side, you can see that the actual code here, the flowlets, and the configuration, which is modeled in Yang, is actually user-written and injected into the system. So this is a component which can be delivered to a customer. The customer can start writing their own flowlets, which is the software which is going to implement their functionality, whatever that is. And the configuration is also injected and provides us with all those nice things with the proper APIs, northbound, and a way to manage the device in a consistent way. So here's some Yang code. So this is the model of the controller. So the Yang, you can compare it to, for example, HTML and the Doom module. So it's like a tree of boxes. So here at the top we have a container called controller, and it contains something. So this is the top in the tree of the configuration tree. So the most important thing here is the listen port. We have to be able to set up a listen port where all the switches are supposed to connect to. Then comes all this kind of switch logic. So there's a list of switch logic. Each switch logic configuration consists of a name, and then we have this data path ID. Either it's a specific one, or it can be any switch which connects. Down here we have the list of all the flowlets in a particular stack, which can be named. So you can have several flowlet stacks, and they are sort of really containing Erlang modules in a list. So they're going to be executed in order according to the order in that list. This container here is empty, doesn't contain anything, because this is sort of an augmentation point for all the flowlet configuration specifics. So all the flowlets have their own Yang models, modeling their own configuration. And that configuration is augmented into the configuration tree at that point. So underneath the flowlet node in this configuration tree, all the flowlets configuration is going to live. So Yang has lots of nice features that, for example, we are making use of. For example, you can see down here that this identity ref here, for example, makes it possible to validate that you can't refer to a flowlet which doesn't exist anywhere. If you don't have a model for a certain flowlet, you can't refer to it in your configuration. So Yang consists of lots of those kind of things, which makes it kind of neat to work with. And here is an instance of the configuration. So it's actually, this is wrong here, should say controller up here. So this is just an instance of the model we saw previously. So here we have the switch logic, and we have given it the name switch. We have said that, okay, for any switch, any data path ID, we should apply this configuration. And down here we have specified the flowlet execution stack with all the Erlang modules that's going to be called. And since we can have multiple flowlet stacks, we have to also define where we're going to start, the start flowlet stack. Okay, it's going to be this one, which we named switch stack. The flowlet container, which was this augmentation point, will contain sort of lots of flowlet-specific configurations. So we can have a look at that on the next slide here. First, we have the model of one flowlet, in this case, the L2 filter flowlet. So it's a container for this, which we name L2 filter. And what it really contains is a list of rules, conditions, and actions for this kind of filter flowlet. So a condition could be, for example, is this an ARP request? Or is the MAC source and dest, are they on the same layer 2 network? Or is it a DHCP packet? whatever you come up with, you can specify a condition here. And when a condition matches, you can do something here in this flowlet. You can pass, which means, okay, continue executing with the rest of the flowlets, or just drop it, or you can go to another flowlet stack. So this is a simplified model of this L2 filter flowlet, and the an example of the configuration could look like this. So we have the L2 filter, we have three rules. One named allow ARP request. The condition is ARP request true? Then go to ARP stack. So we have some kind of flowlet stack named the ARP stack somewhere. And we're going to jump there and start executing that flowlet stack. Another rule saying, okay, are we on the same layer 2 network? Then return pass, and we're going to continue executing with the rest of the flowlets in the flowlet stack. And the last rule, just don't have any conditions, and the action is just drop. So we're going to stop executing the flowlets. Some Erlang code, just showing you a little piece of the sort of Tailflow behavior, which is just sort of defining those kind of functions you need for be able to receiving the events. So like packet in, we'll call the packet in function. And we also can see that there is an init function which is called at startup. So what happens is that your Erlang code connects to sort of the configuration database, extract all the configuration which is specific for this flowlet, and store it in a local state which it returns, and which then will be sort of provided with each call, which is called back into this Erlang module. In this case, we get a packet in, so we get our local state, and we get sort of the message, the packet which came in. And here you can see, here's my middleman, which actually is some that you talked about this. I'm transforming this packet coming in from the wire into an Erlang structure, which I can deal with later on, where I'm executing my rules. So I've sort of implemented this kind of rule engine for this particular flowlet. So there are a number of functions for each of the events. There is this init function, and there is also a configuration change function. Whenever the configuration changes, you can do things, reread the configuration or something else. And the idea is that those flowlets could be, the Erlang modules could be, of course, easily loaded over the network. So if you have a large network with lots of controllers, where each controller is sort of like a network device, from the NCS point of view, we can sort of load and upgrade code the flowlets over the network to all those kind of devices. So I wanted to write this kind of, or implement a little larger example from the first one I did, the programmatic patch panel and the load balancer. So I wanted to implement sort of simulate a data center where you have a n number of racks, where each rack has n number of hosts. You have top of rack switches connected to aggregating switches, and you have a knotted firewall somewhere. So it actually, oh, okay, before I can show you that, I actually have to tell you something else. So I did that with the help of OpenVSwitch. So I have to just one slide to give you an OpenVSwitch prime. OpenVSwitch, as was mentioned before, is a virtual switch, extremely cool little software, which is extremely fun to play around with. So basically, OpenVSwitch makes it possible for you to create bridges, which is sort of Openflow switches, which can be controlled by an Openflow controller. So you can create a bridge, OpenVSwitch bridge. In this case, I call it my gateway. And into that bridge, I can attach network devices on my physical host. So for example, I can add my physical interface, ETH0, on a Linux machine. I can add another bridge, another switch here, and then start a virtual machine connected to that switch. So I start a virtual machine connected to that switch. And then I can simulate something to to simulate patch cables to connect those kind of switches. So in Linux, there is this kind of virtual Ethernet pairs you can create. So basically, you get a network device where you write something at one end, it pops out at the other end, and vice versa. So creating that, you can put the one end into this switch and the other end into the other switch. So then you have a patch cable, and you can communicate from the virtual machine, can communicate all the way through the physical interface. So I made use of that to create this kind of large simulated this sort of data center proof of concept. So this is my physical machine here. I simulate number of racks and number. So each of those boxes here, machines, top of rack switches, aggregating switches, the knotted firewall, the gateway, they are all OpenVSwitch bridges. From one sort of machine, I have a patch cable going to the top of rack switch. So each machine has a patch cable going to the top of rack switch. The top of rack switches are connected to the aggregating switch, which also is connected to the firewall, and then I have this gateway and out from my machine. To the aggregating switch, I also was running a DHCP server so that I were able to start virtual machines on those machines. I mean, connected to those kind of machines everywhere here. They got sort of their IP addresses from this this DHCP server. But the thing is that when you start this, everything is empty. So when this virtual machine tries to send something, it actually will pop up here as an event into my controlling software up here, the Tailflow system. So when a packet enters here, I will sort of, okay, it's a ARP request. Okay, let's install a flow for the ARP request to send it to the top rack switch, and et cetera, et cetera. So basically, all of those switches here were running the same switch logic, the same flowlet stack. This one, on the other hand, was a completely different thing. It actually implemented sort of a knotted firewall, so I could ping, for example, a machine on our local network here, and I rewrote sort of the addresses, etc., taking care of ARP request and matching that with the reply, matching the ICMP request with the reply, etc., to get everything back here. And of course, I had this layer 2 network separation. So the controlling software here was checking that VM were only able to talk to VMs on the same layer 2 network. And that was also done by this general switch logic. So and it actually worked quite well. So that was kind of assuring that it wasn't completely stupid way of implementing Openflow applications. Now, I mean, implementing a thing like this isn't sort of something you want to do, but you want to do something more realistic. And the problem has been that lots of people have talked about Openflow, and it's kind of overhyped. Customers are asking us, we want to use Openflow, blah, blah, blah. What do you have? Do you support it? And we ask, what do you want to do with it? We don't know yet, but probably going to use it sometime. So no one has sort of really come up with some valid sort of use cases. Okay, we have this Google routing thingy they did for some years ago, but apart from that, I haven't really seen that much until recently. So I'm going to show you a use case which is actually a bit more valid. And it deals with something called service chaining. So you have an Openflow switch here. Connected to that Openflow switch, we have the controller, of course, and we also have, this is the logical view here of the traffic, but physically we have network devices like deep packet inspectors or firewalls connected to this switch here. And what we want to do is to chain this kind of services, a deep packet inspector, the firewall. depending on who is sort of where the packet comes from, we might want to send it only into the firewall, or we might want to send it first to the firewall, then to the deep packet inspector, or vice versa. And that is very easy done with Openflow and an OpenVSwitch, where you have full control of the control logic. And this was actually described recently in Ericsson Review this year, number 2 this year. They described this kind of scenario. So when we're using this with NCS, those traditional sort of network devices, they are modeled and managed from NCS, as we have been doing for many years now with those techniques I explained earlier, with these Yang models, etc. And we are configuring those. But we're also configuring this kind of service chain, which we describe as a service model. So service chains has a very high level sort of definition, and it all boils down to a number of operations, both here and there, and also in the OpenVSwitch, to actually realize this service chain. So this is actually a use case which is customers asking for already today. Like I said, Ericsson has written about it also. So I think Openflow has a great use for those kind of specific scenarios where you have certain kind of solutions you want to solve. But in a general case, you will, if you need a firewall, you're going to buy a firewall, of course, off the shelf. You're not going to implement that with the Openflow. So basically, that's my talk. It went faster than I thought. So 5 minutes, great. Any questions? Yeah, the question was if any of the code is available. I'm not sure. I think it would be possible to make it available, but it doesn't make that much sense without sort of the NCS and conf stuff, because management is a sort of important part of the whole thing. The actual sort of architecture is extremely simple. I mean, you just sort of apply those kind of Erlang modules on the events coming in. So it's very simple. But as a whole, you need sort of to be able to deal with Yang modules, etc., and to be able to manage it in a sort of consistent way to actually sort of make sense of it, I think. But yeah.
A question about, you mentioned transactions. I was wondering how those are implemented, and when the user implements some flowlet code, does the user have to be aware of any transactions?
Well, the transaction thing is something which is done within the NCS product itself. And I haven't worked with that part of the system. I kind of new at the company. So I can't really answer your question how they do it. But I know that it works, apparently. So, but that's a very important part to be able to manage a heterogeneous network, to be able to do things in a transactional way and be able to back out. If some device fails, you want to back out everything. And they have solved it in some kind of way, which I can't explain really. So, sorry. Well, first of all, since it's extremely low level. I mean, you can do it, of course, but you have to like reinventing the wheel. You have to take care of everything. You have to. Well, to me, it seems like a waste of time. I mean, there are excellent firewalls you can buy off the shelf, but for certain scenarios, when perhaps you just want to do some kind of small subset of a full-blown firewall, then you can sort of, on a budget, sort of implement it by using Openflow like that. Absolutely. So.
You need to use a different microprotocol to do the same thing?
Sorry?
You need to use a different microprotocol
Yeah, I had different sort of completely different. I had a separate flowlet for actually doing the firewalling and network address translation stuff, and that became sort of rather complex quickly. So perhaps I should have tried harder to try and split that up into minor, smaller parts, if possible. So, I think I at least like the idea of being able to split up the logic into smaller parts and then connect them together. Whether that is a realistic idea in true life, I'm not certain really, since apparently this research from the mid-90s didn't really turn into something, at least something I know of. But well.